Okay, this hour we are going to talk about a new algorithm, which is a tree, decision tree. Okay, the class node is M06. Um, the tree is like this. Okay, we just take a look at the example. Apparently we have four different classes. Okay, we have four colors, and for example, we have x0, we have x1. But think about the algorithm we learned. Um, for the linear regression or logistic regression, they are fitting function, right? They try to fit the data point by using a line or by using the surface or by using a z-shape curve or z-shape surface. But it for um, data set like this, it doesn't look like a fitting line or a surface, right? For SVM or logistic regression, we're trying to find the boundary line, right? So if possible, we can simply just, human beings are smart, right? So we can divide those data points with boundary line, for example, SVM or logistic regression, right? So that is the 50% line, right? Or the boundary line. So we can separate these two data points. And further, we can apply those kind of data algorithm again and try to differentiate those data points. Okay, that is one of the way to do so. But I think we need some other new approach to do such kind of classification, right? So that is tree. Um, so again, um, right here. So if you apply tree algorithm, okay, it may looks like this. Okay, it is just an example. Okay, so again, that is x0, that is x1. Okay, we can first evaluate. Okay, this one, this line. Okay, this line may be x0 equals 2, right? And we can separate this surface, this plane into two parts. Okay, subspace that is x larger than 2 and that is x smaller than 2. Right. So that is how we divide it. Because we're smart, so we know this line would be the better one, would be the best one to cut this space at the first place. Right. And then we may use this one and this one. But you think about one thing. Even if we draw this boundary line randomly or something like this one, even if we know the line right here, okay, is the best line to divide those four classes. But think about one thing. Can we divide them in by using another boundary lines, another set of boundary lines? For example, we can firstly draw this line to separate the dark blue ones on the upper side and all the other right here. And then we use this line to separate the yellow data points and the brown ones and blue ones. And then we use this line to separate the browns and blues. So that means there are tons of way to separate or to make subspace of the original space. There are tons of way. So the problem of such kind of algorithm is not how to correctly divide the space into a proper way. Know that it's not. Because let's take a look at this one. You can you can separate the space in a very complex way like this one. And even though, for example, like this, like the data points right here, we don't know why this data points is right here. Maybe it is an outlier, or maybe it's just some data point which do not collect correctly. So maybe it should be right here, but we don't know. So for the algorithm that divide the space into different subspaces, okay, if you continuously do such kind of separation, okay, you have a lot of boundary line, you can cut or you can separate the entire space into a very, very small subspaces like this one. That is because there is a data point right here. So we cut the space. The original, take a look at this one. The original blue space should be somewhere like here. But because of the dark blue data point right here and the red data point right here, so we can further divide the space, okay, by using some very delicate boundary line right here and here and right here and here, so that the data point in each area or in each subspace will be all the same, right? The data points in this area, they are all dark blue. In this area, they are all red, although they are only one data point. But right here, all the data points in this area will be light blue. So you can continuously cut, or we say separate, set a lot of different boundary lines to do such kind of classification. So at the end, the classification accuracy should be very, very close to 100%, because in each area there are only one color of nodes, right? Okay, so the reason why we call such kind of algorithm tree, that is because that, for example, if we have 100 data points at the first beginning, and again, okay, we can ask a question right here. The question is something like this one: x1, x0, okay, larger than 2, or x0 smaller than 2. So there should be a question that x1 larger than 2. So the answer is yes, and the right hand side is no. So if we draw this boundary line, the red boundary line right here, that is very similar to draw a tree and ask a question on each node. And at the left hand side is the data point, which is x0 larger than 2. So maybe there will be 40 data points right here, and there will be 60 data points right here on the right hand side, because its x0 value is less than 2. So we can do the boundary line again, for example, right here. So that is x1 larger than, for example, 7. All right. So we can ask another question, which is s1 larger than 7. So that is a yes and no. So we can further divide those 40 data points into 2 different subspace. And maybe there will be 10 right here, and there will be 30 right here, and so on and so forth. At each node, we can ask a question about one of the feature, which is x0 and x1 in this example. And we can use that question to divide the area into 2 different subspace, and so on and so forth, so on and so forth. So if you have many different questions to ask, and you will have several levels of the tree. And as I mentioned, if you ask enough questions, you can classify those data points into different color of region with 100% accuracy if you really like this figure, if you really create a lot of boundary line that to classify those data points. But that is not what we expect, okay? Because again, if you really create such kind of subspace right here, and for example right here and right here, if in the future when you collect your testing data, okay, there may be some data right here, because in the training data you have only one data point in this sub area, so you mark them as red, right? But in the future, if there are some data points, blue data point right here, all those blue data points will be misclassified. That is because you create a very specific area for this specific red dot. And again, there's a yellow dot right here, and there's a brown dot right here. So that means you divide the space too much. Okay, I think that is the concept of tree-like algorithm. But the next thing is that no matter how you cut or you divide the space, it seems like you can divide this original space into many small subspaces, right? No matter how you cut. So I think the most important concept of tree algorithm is not to perform 100% accuracy. The idea of tree-like algorithm is that how can you efficiently use less boundary line to classify data points. Again, use less boundary line to cut. So that is talk about efficiency, not accuracy. Okay, so you have to decide. Okay, here for example, I have two dimensions x0 and x1. I should set the boundary line on x0 or on x1 at the first place, at the very first beginning. So the algorithm we'll talk about is how do we evaluate. We should use x0 as the first boundary line, or use x1 as the first boundary line, and so on, so forth, so on, so forth. Okay, so that's I think that is true. So here is an example called Titanic problem. So here we have the data point right here. Okay, we have I think we have lots of passengers on Titanic, the ship. Okay, so that is the y value. Okay, that is the y value. It is a classification problem, so it is either 0 or 1. It is survived or not survived. So we have a lot of different features right here. And as you can see that here we have several features which is not numerical. They are categorical data. Okay, as I mentioned before, for linear regression, logistic regression, and SVM, for those algorithms, because there are some mathematic things need to do, so their features should be numerical. But for algorithm like tree, okay, decision tree, the question you ask at each node, it can be is the passenger is female or male. So maybe the female goes here, the male goes here at that point. So the way you divide the space are not necessary to be numerical. For example, larger than 7, less than 2. It can be a question about categorical feature. Okay, it's a male or it's a female, it's a child or it's an adult. So you can use categorical data on tree-like algorithm. Okay, so we have a lot of data right here. And again, I do a lot of feature engineering right here, so I wish you can take some time to take a look at this part. Because we have only very limited features can be used in this Titanic data set. So right here, I do a lot of feature engineering. That means I create a lot of different new features by using the original features. Okay, take this one for example, title. I create a new feature called title. The title, basically, it need to take a look at the name feature, which is the original name feature. It tries to look up the name feature and see if there is some some strings. Those strings specify it is it has the passenger has certain kind of title. So I create this specific new feature called title based on the name, some string in the name. Okay, because in a later analysis, I would like to figure out if the passenger who has title will have higher survival rate, something like that. Okay, so so that is the feature engineering I made. And for example, right here, okay, the fare and the age is original. They are all numeric data, but I would like to use discontinued, use them as a discontinued feature. So we have several different groups. For example, less than 16, between 16 to 32, and so on and so forth, so on and so forth. So it's really depend on you how to do feature engineering. Okay, and after that, I have a new table. That is the x. That is the y target, and here is the ox, and I make them all numeric. So I simply just take a look at the correlation of the features. So you can take a look at this one. So that is the y value, which is survival. Okay, and we can see that there are two features, which is the title and the sex. Okay, they have higher correlation. Of course, this one is negative, but it really doesn't matter. That means these two features are highly correlated to the survival. So that is what I would like to observe before I perform tree-like algorithms. Okay, so so after that, we can simply just use packages, and we have this one. We simply just give all the x value and the y value to the algorithm, and then we have such kind of a result. So I will teach you how to read the result, but we will demonstrate why tree looks like this later. Okay, so here's the root. So we start from root. So here is the question. That means title. That's then 1.5. The left hand side is yes, the right hand side is no. So originally we have 891 passengers, and we ask one specific question, and we divide those passengers into two subgroups, which is the left hand side and the right hand side. And originally, okay, the people, I think there will be 549 passengers who died, who is dead in that accident, and 342 they survived. Okay, That is the number of the dead and survive. So the total number will be 891. Okay, so after I separate this data point into two subspace, okay, at the left hand side we have 517 data points, right hand side we have 374, and we can see that only 81 out of 517 of the passengers survived. So at the left hand side, more people die at the left hand side, and at the right hand side you can see that there are still a lot of people. We can see that more people, 261 out of 374 survived. So we believe that this question, this boundary line, okay, title less than 1.5, is a nice boundary line because it can help us to classify data in two separate data points. Left hand side we have more dead, and right hand side we have more survived. And of course, and we continue to do that. For example, the next question is this one: family size less than 4.5. Okay, that is yes, that is no. And as we can see that in this subspace, okay, only 10 people survive, but 41 dead. Right? So at the right hand side, again, we ask the next question, and we can divide it into this part and this part. And we can see that that is a very nice question right here, because at the left hand side, all the passengers in this area, in this small area, in this small subspace, okay, 6 samples, but all of them are survived. And at the right hand side, most of them died. And you can continue such kind of thing. If you are not, if you want to do such kind of classification, again, you can simply just ask some other question that can divide those data point again and again and again and again. Okay, it's really dependent on you. Okay, as a model, is a designer or a user, you have to decide how many questions can be asked. And as we can see that because we have the tree, the length of the tree is, the level of the tree is 3, right? Is 3. That means it can only ask 3 questions. But as we can see that there's still some subspace worthy to ask next question to divide those data point, right? So and again, that is how you read the result of a tree algorithm. But still, we have a question is that how do we know title equals 1.5 is the best question we should ask first? So in the following classes, we will tell you how do we decide which variable should be the first question to ask, and what is the value should be used as the boundary line. Okay, so that is how we read. And again, you can use Iris dataset to do decision tree classifier. So again, here's the result and here's the result. It's the same. Okay, it's the same. You can take a look at those things by yourself. You can draw a tree like this one if you. It's just another kind of representation. Okay, so again, I think the most important things about tree algorithm is not how it can perform 100% classification. The problem is, how did you find the best splitting criteria to split the space into two subspaces? Okay, So here I would like to introduce a new concept. Maybe you know that, but it is called entropy. Okay, the entropy, it can be reinterpreted as the level of information, surprise, or uncertainty. So the higher entropy is, that means the data set has high uncertainty. So we take a look at this example, okay? Before entropy, we introduce another concept called information. Okay, suppose that, assume that big X is a random variable. Okay, so I of X, that means the information of X. Information of X. So it can measure the uncertainty of event X. So let's take a look at this one, okay? So if there is a random variable big X, and small x is one of its value, okay? So, and we have the probability, so that is p of small x, okay? So the information of this small x is defined as this one. Okay, let's take a look at this one. That is the probability of x, right? So think about the concept right here. Uncertainty or surprise. Okay, if certain event, it has high probability. Okay, again, if some event has high probability, okay, high probability, that means every time you observe such kind of event, you feel no surprise, right? So high probability indicate no surprise. So low probability event, that means high surprise. So basically the relationship between surprise and probability is like that. So basically we put it right here. When probability is larger, and this value, when probability is higher, this value, okay, this value is smaller. When probability is smaller, this value is higher. So that is the definition of this equation. So and then we simply just put a log value right here. The reason why we use this is because this one, if we have a certain event x, its probability is 1.0. That means every time you collect data from the random variable, and it always small x, so its probability is 1.0. So if we put it in this way, so that should be log 2 1 1.0, and that value is 0. That means no surprise. So the information indicates the value of surprise. So 0 means no surprise. So if certain variable is probability is 0, and that is log 2 1 0. It is strange, right? But the value is plus infinity. That means the probability of certain event is 0. It never happens. But but once if you observe a value of x, it indeed happens, and it surprises you, right? So the information value of this x is infinity, right? So that is the reason why we because you use log, it is much easier for us to use this value, information value. It is between 0 and infinity. So we take a look at this one. So we can see that the value is between the information, the value of of information is between infinity to 0. It depends on the probability of your observation. Okay, so that is good enough. Okay, so that is the definition of information. Okay, and sometimes when you read some material of talking about entropy or information, they use this one. That is because you can put that is log 2 1 px equals 1 log 2 px powered by -1, and that is -1 times log 2 px. So sometimes sometimes you can see that we have a minus right here, and we simply just write the ps in the log, but it is the same. Okay, it's the same. So here we have an example. We have a big event, big X, and the event is 0 or 1. Okay, so the probability is a little bit different. So we can see that the probability of 0, which is the gray circle, is 0.25, and that is 0.75. Okay, so the definition of information is again log 2. Okay, 1 over this one, and that is 2. So the information of the gray event is 2. The information of black event is 0.4. So that we can use some value to evaluate the information when we observe different events. So the higher one, that means more surprise. The lower one means no surprise. That is just a way for us to evaluate the uncertainty of certain event. Okay, so that is information. And the next concept is entropy. Information is for single events, but when we talk about entropy, entropy is for an entire system. For example, if we have 2 events in a system, and how do we evaluate the uncertainty of this event? We use entropy, which is big H. Okay, so here again we have 2 events, which is x equals 1 or 0, and here is the information value 2.0 or 0.415. Okay, so take a look at this one. The entropy of the entire system is exactly the expected value of the information among all events. So we can simply just use this one, that is the probability of certain event times the information of this event, and we sum up all the events. So in this case, we have 2 events, right? 0 and 1. So here we have the weighted information. Okay, the weight is exactly the same as the probability of that event. So that is the probability times the information, probability of x equals 1 times the information of x equals 1. So that is the average information. That is the weighted information. Okay, so that is the definition of entropy. Okay, so again, let's take a look at this one. Okay, if let's take still we take a look at a system has only 2 events. So for this one, probability of an event, okay, if it is equals to 0.5, and we can see that the corresponding entropy of this system will be 1.0. 1.0 means the uncertainty of this system is quite high, because every time you observed the random variable of x, it randomly gives you 1 or 0 evenly. So that you cannot predict what is the next possible value of x, because it is randomly and evenly 1 and 0. So we say that this system has very high uncertainty. Okay, so let's take a look at this one. That means in this system, although we have 2 events, but one of the event has a very high probability. So every time you observe a random variable value, it will give you 1. So it's 1, 1, 1, 1, 1, 1, 1, and so on and so forth. So you can easily predict the next value will be 1, right? So the uncertainty of this system will be low. So the value will be 0. So it's the same right here because it is symmetric. That means px equals 1 is 0. But as we mentioned, we have only 2 events, right? So that means the other event has probability of 1.0. So that every time you observe a value of this random variable, it should be all zeros, right? So the entropy or the uncertainty of this system is 0. And of course, there are some other systems which, has different probability between 0 and 1. So that is how we use entropy to describe the uncertainty of different systems. Okay, so that is entropy. We stop right here because there are some other mathematic things we need to go over, so we stop right here.